Hi, my name is Xingyu Song, and today I'll be talking about our paper accepted to the AutoML conference titled Differentiable Architecture Search for Reinforcement Learning. This is joint work with Yingjie Miao, JD Correys, Dai Peng, Summer Yue, Eugene Brevedo, and Alexandra Faust, all of whom are part of the Google Brain team. To begin, I will first talk about the background and motivation behind our paper. DARTS has become a very popular neural architecture search method for supervised learning recently, with multiple variants topping leaderboards on typical benchmarks, such as C410 and ImageNet. DARTS is particularly attractive for reinforcement learning, as DARTS is a very simple and modular technique. Hypothetically, it can very easily integrate into any large and distributed RL pipeline, such as Q-learning and policy gradient methods, as one would only need to replace the RL network architecture with the DART supernet, but run everything else as normal. What is shocking, however, is that this avenue of thought has almost never been explored previously. This is where our paper comes in order to validate these hypotheses. However, before we jump into the details, we first need to discuss why NAS for RL is now an important and new frontier to tackle. As RL progresses in maturity applications, so do the size of the architectures. For example, in the ProcGen paper, it was discovered that a large residual architecture, termed Impala CNN, possessed very strong generalization performance. Furthermore, in robotics applications here at Google, in particular for grasping, very large architectures with over 15 different convolutional layers are used to process high-resolution images. We suspect that custom architectures specific to these tasks could strongly help improve both performance and latency for RL applications. While some related work has been done in NAS for RL, virtually all of them, however, use black box or evolutionary optimization techniques which do not utilize backpropagation. These include the classic NEAT method for evolving policies for domains such as continuous control, like Majoko. However, such methods typically cannot scale when optimizing over tens of thousands of parameters. Vision-based RL regularly uses policies which have over 1 million parameters, and thus such techniques are not appropriate for larger scale RL. I will now talk about how we set up DARTS for RL. I will provide a brief overview of the main idea of DARTS. This can be explained in a 4-step process from the figure as shown. In A, the user forms their search space, which specifies the possible connections between tensors or nodes in the graph, as well as the possible operations used for each connection. In B, all possible operations are enumerated and their outputs are combined using a softmax-based weighting and put into what is called a supernet. In C, both the weights and the softmax variables in the supernet are trained, which leads to some operations being weighted more than others. Finally, in D, we prune the softmax variables to find the best connections and operations to use for a discrete architecture, which is trained again for evaluation. When applying this to the RL scenario, however, there are a few challenges and issues to examine. The first main challenge is that as opposed to supervised learning where the dataset is fixed, in reinforcement learning, the data always changes. The data is generated based on the current policy performance, and thus training can sometimes fail when there's a negative feedback loop in which a poor policy generates even poorer data to train from. This can potentially occur in the DART scenario, as the supernet might not be able to train, for example if the softmax variables accidentally routed bad operations. The second challenge is that the loss function in reinforcement learning is much more complicated than the supervised learning loss. As the loss function is the only signal for training the softmax variables in DARTS, it is unclear how many of the auxiliary losses in reinforcement learning would affect the softmax variable training. This is especially true for certain losses, such as value function losses and entropy bonuses, which are not relevant during evaluation time, which is the final objective we care about. In any case, we will see what happens when we apply DARTS to RL. One necessary change we will make is to focus only on uni-level optimization as opposed to bi-level optimization, which is used in SL DARTS. This is because bi-level optimization is notoriously unstable and requires multiple improvements to get working, and may confound the message of our paper. Furthermore, one of the main objectives in RL is to optimize sample complexity and asymptotic reward anyways, which uni-level optimization conveniently attacks. In our setup for the supernet, we will apply a typical normal and reduction cell stacking. The entire network will be composed of D blocks, with each block consisting of N normal cells, which preserve the input shape on the output, and R reduction cells whose outputs will be a factor smaller than the input. For the search space construction, we construct a so-called micro search space, which will be used for the rainbow and SAC algorithms. The micro search space contains the conv3x3, ReLU, and 10H operations. We also use a more classic search space for the PPO algorithm. The operations here are from the original Darts paper and contain convolutions and dilated convolutions of different kernel sizes, along with a ReLU nonlinearity. Both search spaces are then appended automatically with the skipped connection and zero operations, which are required for any Dart supernet. Here, I will show the core end-to-end evaluation performances of discrete cells after the entire search process is done. We begin by showing the most surprising result, where we are able to find a single cell over all 16 project games, which is competitive with, and sometimes even substantially outperforming the Impala CNN baseline. To find this cell, we trained our Supernet simultaneously over all 16 ProcGen games. On the left-hand side, we already see that even the Supernet is outperforming the Impala CNN baseline. On the right are the final training curves for the discrete cells. Furthermore, on the PPO case using the classic search space, we find that we are also able to find competitive performance against the hand-designed baseline. One thing to note is that the random search significantly underperforms here when performing a fair comparison based on the total wall clock time. One natural question to be raised is how difficult the search space really is. In order to answer this question, we performed a large random search using a budget of 100 cells over the two games Dodgeball and Maze. Surprisingly, we found that over 50 random cells obtained trivial rewards on Dodgeball, and thus suggests that the search space is quite difficult. Both Impala CNN and Darts are ranked at the very top, however, and this suggests that Darts is performing already very strongly as a search method. Lastly, for SAC, a third algorithm we tried, we also find consistent improvements over the baseline encoder, showing the promise of Darts on a different RL domain. I will now present extensive ablation studies to verify that all parts of Darts works as intended. We first look at how the Supernet trains. For PPO, we see that the Supernet produces reasonable rewards against the baseline, and furthermore, that softmax weighting converges to reasonable operations. Following up on the softmax weighting, we found that 3x3 convolutions were weighted strongly over 5x5 ones for the Dodgeball environment. We wanted to verify whether this suggests that 3x3 operations are indeed better than 5x5 operations, and thus we manually also trained policies using 3x3 or 5x5 operations. We verified that this is indeed the case on the right-hand side, and this suggests that the Supernet is correctly weighting better operations. In parallel with PPO, we also show a similar Supernet training for Rainbow, also verifying the trainability of the Supernet and the convergence of the softmax weights. One sanity check we needed to make was to see if poorly set up Supernets would train. This was indeed the case, as if we removed the ReLU nonlinearity from convolution operations, the Supernet would not train. Furthermore, we wanted to see if the softmax architecture variables are properly routing operations. We thus trained a uniformly frozen architecture variable and also found that this led to an untrainable Supernet. Another important ablation we made was to study whether throughout the Supernet training the corresponding discrete cells are improving. We found that this is the case. At the beginning, if we discretize the Supernet, we find a lot of skip connections circled red. This architecture is clearly a poor design. At the end of the training, however, we see many 10H and ReLU connections circled blue. This looks more like a reasonable design. Furthermore, if we discretize the Supernet throughout training and get a sequence of cells, then train them from scratch, their final performance increases. We also found that the Supernet's training is crucial for producing good discrete cells. For example, if we discretize a poorly trained Supernet, then the corresponding discrete cell performance is low, and the design also does not make sense, as it possesses no convolutions. If we discretize a properly trained Supernet, then the corresponding discrete cell performance is high, and the design does make sense, as it has a balanced use of convs and nonlinearities. Lastly, we found that after normalizing against the baseline to reduce confounding factors from the environment, there is a strong correlation between Supernet and discrete cell performances. In conclusion, we found that softmax routing even works for RL, and that it leads to better architectures. This is one of the first applications of Darts outside of regular supervised learning. We believe that this has numerous potential benefits for RL domains, such as continuous control, vision, robotics, and games, for improving sample complexity, efficiency, generalization, and adaptation. Here are the links for the archive version of the paper, the open review, and the code. Thank you.